This is a generic operational amplifier, simply referred to as an OpAmp. The OpAmp is this triangular shape object here. It has two inputs. One has a negative sign, the other a positive sign. The one with the negative sign is called the inverting input. The one with the positive sign is called the non-inverting input. And the end of the triangle here is called the output. Now, generally only the triangle is shown, but it should be understood that there are several connections here which are generally not shown on the schematic. One would be, of course, power for this op-amp, and there are several different ways it can be powered, but the most common is to have a positive supply, also to have a negative supply, and in many cases, there will be someplace in the circuit a ground connection. So these three connections, positive supply, minus supply, and ground, are typically not illustrated, but it's understood that they are needed in order to make the circuit work. Now, in the simplest case to analyze, and I think the one which shows the most insight as to what the circuit is really capable of, is if we have two types of resistors, R1 going into both inputs, and R2. R2 goes from the input, inverting input, to the output, and R2 also goes from the non-inverting input to some sort of reference voltage. So in this case, we'll illustrate that this op-amp can have three inputs, V1, V2, V reference, and an output, VO. There are a few simple rules that we should be aware of to understand how this circuit works. And that is that this op-amp is very, very close to an ideal amplifier. So therefore, we'll just write down a couple of these rules. The first one is the inputs draw no current. So the positive is the non-inverting and the inverting inputs draw no current. Now they do that because they are very, very high input impedance. The second rule is that the output impedance is zero. So if we put a load across here, even if it was a very small load, it would make no difference. That's to say that we couldn't load the circuit down. We put a kilo ohm here, we put 1 ohm here, it makes no difference. Now, within reason, of course, that's not entirely true, but it's true for the vast, vast majority of cases of circuits that we're going to be looking at. And the third rule is a very, very interesting one. These two are simply rules which correspond to any ideal amplifier. The input has infinite impedance, the output has zero impedance. But the third rule is peculiar to op-amps, and that is that these two input voltages here, the inverting and non-inverting inputs, are equal. So there it is. The non-inverting and inverting positive and negative input voltages are equal. That's to say that the op-amp will do everything in its power to make these two equal. If we perform some sort of analysis and it turns out that they're not equal, then it means that the op-amp is saturated or is not working properly. So to put this mathematically, we could say that the voltage at the inverting terminal is equal to the voltage at the non-inverting terminal under normal operating conditions. So with those three rules in mind, we're going to go ahead and see what this circuit is capable of doing. First of all, we're going to take a look at the voltage right here at the non-inverting terminal, and we're going to do this by means of superposition. So by superposition, we can say that the voltage at this terminal is equal to this voltage times this resistor over the sum of these two resistors. And we can say that because we assume that the other voltage here is 0. So we're only going to look at the contribution at this point due to V1. So it's equal to V1 times R2 over R1 plus R2. But of course there is a contribution to the voltage at this point from this source. So now we'll put this source to ground, V1, and we'll look at the contribution from VO. Plus VO times, and this time it will be R1 over R1 plus R2. And we'll do the same thing over here. We'll find the voltage at the non-inverting input, the contribution from V2. So that will be V2 times R2 over R1 plus R2 plus contribution from Vref when V2 goes to 0. So Vref times R1 over R1 plus R2. So this is just simply Ohm's law. This is the voltage divider rule, and the voltage divider rule applied from both ends, and this is called the superposition rule, and we could use this principle for many inputs as we have available. So now we're going to do something very interesting. We're going to apply rule 3. We're going to say, but the voltage at the inverting terminal is equal to the voltage at the non-inverting terminal. So we're going to rewrite this. I should have said this is a V1 here. We're going to say now that V1 is equal to, V1 times R2 over R1 plus R2 plus VO times R1 over R1 times R2 is equal to all of this, which is V2 times R2 over R1 plus R2 plus Vref over R1 times R1 plus R2. All right, so right off the bat, we notice something interesting here. All these denominators are the same, and so they cancel right out. So we end up with a great simplification here. V1 R2 plus VO R1 is equal to V2 R2 plus Vref R1. So now what we're going to do is we're going to solve for VO. So VO R1 is equal to V2 R2 minus V1 R1 plus Vref R1. And now we can divide everything through by R1. So VO is equal to V2 minus V1. So I brought this over. This should have been a V1, V2, R2 rather. So this is R2, and that didn't look right. Over R2 over R1 plus Vref. And this is the equation of the output of the generic OpAmp. Now, notice what we can get out of this. We can get several different kinds of amplifiers. We can get out of this a difference amplifier. So let's just make a note. Types of amplifiers. The first obvious type is a difference amplifier. A difference amplifier, and that we get if Vref is equal to 0. So notice what happens when we get VO is equal to V2 minus V1 times R2 over R1. it amplifies the difference between these two voltages. Now, let's say that we wanted to get a positive amplifier. And to do that, we would simply say, let V1 equal Vref equals 0. So what do we get then? We get VO equals V2 times R2 over R1. It's a positive amplifier. And let's say that we wanted a negative amplifier. Well, then we would let V2 equal Vref equals 0. And then we would get VO is equal to minus V1 R2 over R1. So here we can see that we can have some very, very interesting configurations with a minimum amount of effort. The difference amplifier is very useful if you have very high common mode noise, such as you might have in let's say, in a recording studio or something similar. These amplifiers, of course, are just like any other transistor amplifier. Now, besides that, in each case here, we've had V reference set equal to 0, but there's no need to do that. We, in fact, could let the reference be any voltage. So the fourth type of amplifier that we'd have is all of the above plus a DC offset. And there are many times when that is quite a useful feature to have.